Hello guys. This is the fourth method on how to solve ordinary differential equations. We have seen how to solve a separable method, using integrating factors, using a homogeneous method. Now we have the exact differential equation. So maybe I'll just explain something. So I've introduced a concept on implicit differentiation. Now we had a function, then we implicitly differentiated it to get our derivative on the lower side. Now, what if that is in calculus 1? What if we want to get now the original solution? How will we get back to the original solution? Because in calculus 1 we don't have a method on how to get back. We have differentiated differentiated the first equation up to its derivative. Now getting back, we'll have to use calculus 2 process on how to get back to our original function. So we are saying we're using exact differential. Now the first order derivative, the first order ordinary differential equations given as m of xy dx plus n of xy dy equals 0 is said to be exact. Exactly only if the derivative of m with respect to y, and keep in mind this is the second derivative. Okay, so again I'll take you back to the Alexis Claude's theorem. I had introduced it earlier for this purpose. Now we're saying the derivative of m with respect to y should equal the derivative of n with respect to x, which is the same as this. Now, so this is our second derivative. Keep in mind the reason is because we are saying already it has been differentiated with respect to x. Now if you differentiate with respect to y, you should get the same as we have already differentiated with respect to y. Now we are respecting it with x. Now, so this is Alexis Claude's theorem. So check my video. I'll give that video to this description. So that's the theorem we'll be using to determine whether a differential equation is either exact or non-exact. Then following videos will look on how to solve these exact ordinary differential equations. Now we're saying if m of x of y dx plus n of x y dx equals 0 is exact, then there exists a potential function. Now these are original function. Okay, so these are original function. Say for example I'm given 2x plus 3y, okay, equals 0, for example. So I'm given these, then I use implicit differentiation to get to my dy dx as for example, for this case we'll get, for us to get our dy dx, we'll get negative we just get negative 2 divided by 3y. Okay, so for this case this is our implicit differentiation. Then so if, okay, let's perform this. If I take this, if I differentiate this is 1, so it should be 3. It should be 3 alone. Okay, so it should be shouldn't have a y at this point, so it should be 3. So our dy dx is 3. Now once we have implicitly differentiated to this point, how can we get now from this derivative back to this? Now this is where we use exact differential equation. Now we are saying if the m of xy dx plus n of xy dx equals 0 is exact. Now there exists a potential function. This is our potential function, original function, such that if you take the derivative of that function should equal this expression. Now we're saying the derivative of x, the derivative of f of xy equal the derivative of f with respect to x multiplied by the dx plus the derivative of f with respect to y multiplied by the dy. Comparing these, we are getting our m of x as the d of f divided by the d of x. Now, and again, we're getting our n as this. Now, because we are saying m of x y dx, added that to n of x y dy equals 0. Now, the derivative of our potential function, so this is our potential, the derivative of this potential function equals 0. Now we'll get a general solution that this potential function equals to a constant. Okay, so the potential function equals a constant. Now, once we have this knowledge, now let's look an example on how to solve an ordinary differential equation using the exact method for us to get these concepts right. So please like, share, and subscribe to my channel. Thank you.